Hello, and welcome to the short course on models of social dynamics. I'm Paul Smaldino. I'm an assistant professor of cognitive and information sciences at the University of California, Merced. In this unit, we'll tackle coordination and norms. Okay, so let's talk about the problem of coordination and norms. So, cooperation was the focus of the last unit. But cooperation is not the only problem to be solved for social cohesion. Once we have decided to cooperate, we have to figure out how to do so. Uh, how do we best cooperate? Who are the best cooperators for me? If we don't understand one another's intentions, don't have the same goals, don't do things the same way, cooperation can be impeded. So there's lots of important considerations. We want shared goals. We want common ground for communication. We want shared intentionality and a group mindset. We want empathizing, the ability to empathize with others' feelings and experiences. And in a lot of times, what we actually want is similar backgrounds, experiences, and traditions to help coordinate interests. Now, obviously, cooperation and coordination can work without these things, but sometimes it's helpful for at least some of these to be present. Um, More generally, what we want is the ability to do things in the same way. And doing things the same way is what we'll call coordination. So, a prominent example of coordination is language. Many of the words we use for things are arbitrary, but unless we use the same words for a given situation, we're liable to have a misunderstanding. And of course, that can occur regardless, but it makes things worse. In most of the world, cars and trucks drive on the right side of the road, but in other countries like the UK, Australia, and Japan, cars are driven on the left. It doesn't actually matter what side you drive on, only that everyone does things the same way. Um, so throughout this, I'll use the word norm to indicate behaviors that facilitate coordination. Now, the word norm is used a few different ways in the social sciences, but here, I'll use it this way to connote behaviors that facilitate coordination. Norms differ from one population to another, and they can also appear to be fairly arbitrary. In this unit, we'll focus on the spread of norms. Um, Sometimes norms can actually serve to signal to others a larger suite of norms that might be harder to observe. So, if you go to an academic conference and you are male, you are probably likely to wear a tie or at least a jacket if you're an economist, but probably unlikely to do so if you're an anthropologist. The tie, or lack thereof, doesn't serve any function directly, but it does signal to others the sort of person you are likely to be. Likewise, norms often develop among communities or groups of friends that enable rapid communication between their members, but might be baffling to others. So this example comes from the oatmeal comic that illustrates differences in style between the east and west coasts of the United States. So let's talk a little bit about prosocial norms. So norms may often be arbitrary, but that doesn't mean that all norms are always just as good as any other norms. So some norms, like smoking cigarettes together after vigorous activity, let's say, can be directly harmful. Other norms can be prosocial and improve the collective good. So some examples are rules against murder, good things, and assault, also a good thing. These encourage civil order and make us feel relatively secure. Property rights allow and encourage productive effort and innovation. Well-managed taxation provides roads, schools, and other public goods. Product standards, building codes, and rules of professional conduct allow more efficient commerce and protect citizens from harm. And norms governing the filling of political offices reduce the chance of a civil war over political disputes, hopefully. So in any given domain, there are many possibilities for exactly what norms to put in place. Drive on the right or the left, speak English or German, wear a business suit or yoga pants and flip-flops, allow disputes to escalate, or prohibit violence. Some norms may be more in line with basic human psychology and practicality than others. For example, we can probably take driving in swirly spirals off the table, but in other cases, it's clear that many options are possible. Human cultural diversity is a testament to this fact. So, how might norms spread or dominate? In this unit, we're going to tackle this question with a few models. In a sense, this question combines our first two units on the spread of behaviors or opinions with the previous unit in which the utility of a behavior depended on the behavior of others. Again, we're going to use an evolutionary framework with success-biased transmission. That is, we'll assume that individuals interact with others using particular strategies, and that those interactions lead to some payoffs. Afterwards, individuals will have the opportunity to observe others and switch to a strategy that is more successful. So we could also use other social learning strategies, such as a conformist strategy, in which an agent copies the most common norm. This sort of thing is left as an exercise. So to start, we're going to consider an example in which two norms compete and in which neither has any intrinsic advantage. Let us consider a coordination game with symmetric payoffs. So here's a two-player game, and here's the payoff matrix. Again, the payoffs here are to the row player. This is a two-strategy, two-norm game. So when considering competition among strategies, the simplest thing to do is to start with two. So let's imagine a population in which everyone uses one of two norms in their social interaction. In this simple coordination game, each agent uses either norm 1 or norm 2. This is not a cooperative dilemma. It is always better to coordinate than not, and even non-coordination is cooperative and therefore yields a positive payoff. In fact, we can assume in this scenario the dilemma of cooperation has been solved. That's one way to think about it. And now the issue is how to maximize the benefit between potential cooperators. So here, this is a symmetric coordination game in which coordination on norms always yields a benefit delta over non-coordination. So without any loss of generality, the baseline payoff is set to 1. So delta is basically the bonus for coordinating. Let's talk about payoffs. Individuals in this model have many interactions with members of their communities during which they accumulate payoffs. So we're going to do things a little bit differently, in part just to explore different possibilities of the way models are constructed. So in the prisoner's dilemma simulations in the last unit, we had individuals play with a small number of individuals to accumulate payoffs, and then they always copied the strategy of their best performing neighbor deterministically. So we could do that here as well. But it's worth noting that that is, in fact, an arbitrary modeling assumption to some extent about how interactions and observations are structured. So let's try something different here. Let's assume that every individual has a lot of interactions in which there is an opportunity to coordinate. In this case, we don't necessarily need to simulate all of these interactions explicitly. Instead, if we know the distribution of strategies in the population, we can just calculate the expected payoff under the assumption of random interactions. So remember that agent-based models are great for exploring assumptions of non-random interactions, but it's also important to establish a baseline. So, how do we do this? To calculate an agent's payoff, we just need to know the proportion of other agents who do and do not share the agent's norm. So let's let n sub 1 be the number of agents who use norm 1, and n sub 2 be the number of agents who use norm 2. So in a population of size n, n sub 1 plus n sub 2 equals n. The payoff to an agent who uses norm 1 is determined by considering the expected payoff over time if interaction partners are random from the population. So this is an equation. The first term basically says that the payoff is the number of agents with norm 1 times the payoff for norm 1 times plus the proportion of agents with norm 2 times the payoff for norm 2. So this equation reduces to this, 1 plus n sub 1 minus 1 divided by n minus 1 times delta. And the same is for the payoff for norm 2. Right? Just replace the 1s with 2s. This makes sense and is intuitive if you examine it a little bit. It basically says that the payoff is the baseline of 1, because you get 1 from interacting with anyone. That is just the payoff for cooperating with someone. Plus, you get the coordination bonus times the proportion of the time that your interaction partner uses the same norm as you. And it's n minus 1 minus n sub 1 minus 1 divided by n minus 1, because the agent in question can't interact with itself, right? Okay. So now it comes time for imitation. So we used those equations in the last slide to calculate the payoffs. Now, each agent is going to select one other agent at random, just like before, and compare their strategies and payoffs. If we stuck with the assumption we used in the previous unit, deterministically copying the best strategy, then whatever norm was more popular would be instantly adopted by everyone. So this is a valuable thing to realize, right? In the prisoner's dilemma game, focusing only on local interactions influenced and slowed the spread of behaviors. Here, we use the expected payoff, so we ignore the heterogeneity added by local interactions. But we will add heterogeneity in another way. So instead of assuming deterministic copying, we're going to make what is probably a more realistic assumption a lot of the time, that copying is probabilistic. Here's why I think probabilistic copying makes sense. If your payoff is higher than mine, if your payoff is a lot higher than mine, I should be very likely to copy you. If your payoff is only a little higher than mine, then I should probably be more likely to copy you than not, but also still somewhat likely to stick with my current strategy. And if your payoff is worse than mine, I should generally stick with my current strategy. But every now and then I might make an error in judgment or want to explore and try something new, so I'll still occasionally copy a worse strategy. Luckily, there is a functional form that fits this description nicely, and that is the sigmoid function. So here's the equation, and here is a plot of this where the payoff difference on the x-axis is just x sub j minus x sub I. So here, in this scenario, an agent I with payoff x sub I observes agent j, payoff x sub j, and considers their relative payoffs. And to the extent to which, if they have the exact same payoff in this model, then it's a coin flip whether or not 50-50 chance that I'll copy the other agent, that agent I will copy agent j. If the difference is positive, if agent j has a higher payoff than agent I, then agent I has a higher than 50% probability of copying agent j, and vice versa. If agent j's payoff is lower, then agent j will probably not be copied. There is this scaling parameter alpha, which controls how quickly small differences become important. It basically controls the slope of that line in the middle that goes from low to high. For simplicity, we'll use alpha equals 1 in our model code. So let's look at the code. So let's look at our model is going to be coordination underscore simple dot nlogo. Here we are. Right. So we've got sliders for init norm 1. That's the frequency of norm 1 in the population at the beginning of the simulation. And coordination benefit, that's our delta. That's how much more coordination. That's basically the bonus for coordinating. We can look at the code. Well, here, let me just also say that this plot is just going to be the frequency of norm 1 in the population from 0 to 1. So our code looks like this. Each agent keeps track of whether or not it uses norm 1. If it uses norm 1, this will be true. If it uses norm 2, this will be false. and it keeps track of its payoff. In the beginning, just as before, each patch sprouts an agent, and with probability in it norm 1, the agent is set to have norm 1 and norm 2. It's then recolored so that norm 1 agents are yellow, norm 2 agents are blue. Okay. In the dynamics, in the go procedure, we stop if all the agents are using the same norm. Then we calculate payoffs. This works very much like the prisoner's dilemma model. So here, though, instead of every agent interacting locally, we just calculate what the payoffs are for norm 1 agents and norm 2 agents using the equations we just discussed in our previous slides. And then we assign all the payoffs with norm 1, the norm 1 payoff, and all the agents with norm 2, the norm 2 payoff. Then when agents copy others, an agent looks at one other agent picked at random and compares their payoffs, and then copies them with a probability derived from their sigmoid function. And then agents are recolored according to their norms. And that's the model. So first, let's look at the case where there's no coordination benefit. In this case, actually, there are no differences ever between agent payoffs, right? So both norms can persist indefinitely because the frequency of each norm over time is essentially a random walk. In the long run, one norm will probably go to fixation just by chance. This is a process called neutral drift, but this can take a very long time. Basically, agents are just switching strategies totally at random. Now, let's put a little benefit. As soon as there's really any benefit to coordination, the more common norm will almost always spread. So if we let norm 1 start at 60%, it goes to fixation. If we started at 40%, norm 2 goes to fixation. When it's right in the middle, who knows, right? This will go one way or the other about half the time. But in general, the most common norm is always going to be favored. So when there's any benefit to coordinating, the more popular norm should spread. That means that if uncommon norms persist, there must be mechanisms beyond coordination, or the assumption of random interactions may not be met, or there may be differences in payoffs between the two norms. So for our purposes, we've established a baseline model that illustrates dynamics of norms when those norms are arbitrary and neither is intrinsically better. But now, let's relax that assumption and consider the case where one norm is clearly superior to another. Will that norm spread? So now we're going to look at what are sometimes called group beneficial norms. Things get interesting if we consider two competing norms in which one norm is group beneficial or prosocial. It's better for the group, but it carries a cost when rare, since if it's rare, then others will fail to coordinate. So consider this payoff matrix for an asymmetric coordination game. Norm 1 here is the group beneficial norm. Those employing norm 1 confer a benefit G on everyone regardless of their norm. So norm 1 is also prosocial because it contributes to everyone regardless of what norm everyone is using. There's also an additional benefit, delta, of coordinating on norm 1 that isn't now present when coordinating on norm 2. So coordinating on norm 1 is obviously preferable to coordinating on norm 2, and it's pretty clear that if norm 1 is common, then anyone using norm 2 should switch, to receive the additional benefit delta, and also G. However, to make things more interesting, norm 1 also carries a cost when it's rare. So norm 1 may be costly to implement, it might be burdensome to execute alone, it might be actively punished by some non-users. All these are real possibilities for uncommon behaviors. And we'll model this just by imposing cost H to employ norm 1 when one's partner uses norm 2. So, like I said, it's easy to see that this prosocial group beneficial norm should persist when common. In the language of evolutionary game theory, norm 1 should resist invasion by rare norm 2 agents. It should be evolutionarily stable against norm 2. And that, I think, doesn't really require explicit simulation to see, although we can try it, and you're welcome to do so with our model code. But the real question is, how do costly prosocial norms spread when they're rare? To tackle this, now we're going to need to use the model. We need to update it to reflect this new group beneficial payoff structure. So we'll look at IS. I should say we'll look at coordination with asymmetric payoffs, which is coordination underscore asymmetric and logo. All right, now we see a few things. We've got a few more sliders. We've got the proportion of norm 1 initially, that's the same as before, but now instead of just one payoff slider, we've got 3. Our group benefit, that's going to be G. Our norm 1 self benefit, that's going to be delta. And then, so G, remember, is the benefit to everyone that users of norm 1 confer, regardless of what norm you use. This is delta, that's the benefit of coordinating on norm 1. And then the norm 2 deviance cost is H. This is the cost of using norm 1 when one's partner uses norm 2. Okay. And we've just, all we have to do here in our model code to update this is just change the payoffs to our updated payoff matrix. We'll also notice a couple of boxes here, and I'm going to talk about it in a little bit, okay? But you can ignore them for now. So let's start with some arbitrary values. Delta equals G equals 1, and H equals 0.5. So let's let our initial frequency of norm 1 be 0.5. In this case, it was a coin flip before, right? When whether norm 1 and norm 2 would spread. And here, okay, it spread. It spread. And it turns out it'll always spread. Let's lower the frequency to 0.4. Now remember, when the payoffs were identical between the two norms, and it was symmetrical, the dominant norm always spread. So norm 1 would never spread if it started out as only 40% of the population. But look, a group beneficial norm can spread even when it's less than 50%, even when it's the less common norm at some point. So it seems to spread even when rare. That's awesome. What happens if we keep lowering it to 0.3? Not so lucky anymore. All right. Now norm 2 dominates. So what's going on? Right? If you play around with the payoffs, and I encourage you to do so, you'll find that this that there appears to be a threshold above which norm 1 will tend to spread and below which it doesn't. And that the threshold might move depending on the values of the payoffs, but there always does seem to be a payoff below which norm 2 spreads. So let's take a look at why. So, in general, I have avoided mathematical derivations as much as possible for this course and stuck to insights that can be gleaned from simulations. However, in this case, it's pretty easy to calculate exactly where the threshold is, so we're going to do it. This is going to be an approximation for which we will assume a large enough population where the difference between n and n minus 1 is negligible. Which is actually a fairly reasonable assumption for our model because we have enough agents, several hundred. So let the proportion of agents using norm 1 be p, so that the proportion using norm 2 is just 1 minus p. The expected payoff to an agent using norm 1 is going to be the proportion of times it receives a coordination benefit plus the proportion of times it pays a non-coordination cost. So p proportion p of the time it interacts with another norm 1 agent, and it gets that nice cushy bonus, and proportion 1 minus p it interacts with a norm 2 agent, and it pays that cost h. The expected payoff to a norm 2 agent is calculated similarly. Proportion p of the time it interacts with the norm 1 agent, and it gets that nice prosocial benefit, and then proportion 1 minus p it interacts with another norm 2 agent, and it just gets the sort of regular baseline. So note that both agents do better when they interact with norm 1 agents. When is norm 1 going to spread? It's going to spread when the payoff to a norm 1 agent is greater than a payoff to a norm 2 agent on average. And I've just rewritten the payoffs here again. So let's just set these two things. Let's just do some math and set v1 greater than v2, and then solve for p star, which is going to be the threshold frequency above which norm 1 spreads. So here I've just written the two payoffs out, one on each side of the greater than sign. So we're going to solve for when the payoff to norm 1 on the left side is greater than the payoff to norm 2, the right side. You can do a little algebra and notice that a lot of things cancel out. Again, I encourage you to work through this yourself. Sometimes our algebra muscles will have atrophied, and it's worth stretching them out and moving them around a little bit. Okay? Let's keep doing this. This reduces to this. Now let's get p all on one side. And we solve for the case where for norm 1 to spread, for the payoff for norm 1 to be greater than the payoff to norm 2 on average, p has to be greater than p star, which is this h divided by delta plus h. And if you look back at the NetLogo model, you'll notice that I've added this little box, this little monitor, and that displays, it automatically calculates and displays the threshold based on the model parameters. So for the parameters we used in our initial exploration, we see that the threshold is 1/3, exactly what we observed. And to illustrate this in a little more depth, I actually ran 100 simulations under these exact parameter values for different initial frequencies of norm 1, and then plotted the proportion of those runs in which norm 1 ended up dominating. So how many out of 100? And you can quite clearly see the dividing line, right? Exactly where p star is, that's where we get the line from norm 1 dominating more than half the time to norm 2 dominating more than half the time. A few things are illuminated by this calculation. Okay. First, the threshold for norm 1 to spread is lower when the benefit of coordinating on norm 1 is stronger. So delta. When delta is higher, p star becomes smaller. Second, the threshold is higher when the cost of using norm 1 with a norm 2 agent is greater. So when h is larger, p star is larger. So these results make sense. Even rare interactions may be attractive if they have a high payoff, but the benefits have to outweigh the costs of non-coordinating interactions. There's a third thing we learn, which is that the prosocial benefit, G, generated by norm 1, is totally irrelevant to whether or not norm 1 spreads. It can be large, it can be zero. It has no influence on the spread of norms in this model. And the reason is apparent if we think about it and compare the equations that we saw for the expected payoffs. Right? Norm 1 agents provide the benefit G to everyone in the population. So G plays no role in differentiating the payoffs of the two norms. Everybody gets G. How much G they get is a function of how many norm 1 agents there are. So the population does better as a whole the more norm 1 agents there are. But it doesn't help differentiate between agents in the population. This indicates, to some extent, that we've modeled a norm that is better during coordination, but costly when rare. The prosocial nature is an afterthought. 2 comments here. 1, we're often interested in how norms that are better for the population but costly when rare can spread, even if they're not explicitly altruistic or prosocial. So that's fine. Second, the model, I'd say, does teach us something about the spread of prosocial norms, which is that their spread probably depends primarily on the costs and benefits of coordination and non-coordination, rather than the group level benefits they confer. Now, there are probably cases in which that is not the case, and the prosocial nature of the norms do in fact matter to their spread. But it requires an analysis of the assumptions that we need to make, which is one of the things that's valuable about modeling. Another thing you'll notice is that by looking at this graph is that norm 1 doesn't always spread when its initial prevalence is above the threshold. It just spreads more often. That's because there is stochasticity. It's probabilistically more likely for norm 1 to spread when its initial frequency is above the threshold, but because of randomness baked into the model, sometimes the population will dip back down of norm 1 just by chance and get low enough so that norm 1 vanishes, and vice versa. This indicates that the results of models should be taken as indications of probable outcomes and definitely not as indications of certain outcomes, right? Almost always. Unless our model is extremely precise in terms of the assumptions it makes and the mapping between real life and reality. Okay, so a major thing we've learned from the model is that if a prosocial or better norm, group beneficial norm, is not sufficiently common at the outset, it will probably not spread, but disappear. This might be a little depressing. So, what if we what if we introduce a superior norm that, if adopted, will make us all better off, right? We want that to spread. Surely it will, right? The model suggests otherwise, that unless a sufficiently large faction can be coerced to adopt the new norm to demonstrate its clear superiority, it's going to fizzle and die. Is there any other hope for the spread of new beneficial norms? Right? It seems like a paradox. Something that is clearly beneficial won't spread because when it's rare, it can't demonstrate its benefit. Is there any hope? Yes, hopefully. There's several possible mechanisms that researchers have identified for the spread of rare norms. And in this unit, we're going to tackle one of them. So we've assumed so far, actually in all our models we've assumed this, that we're dealing with a single population of interacting agents. However, humans are structured into groups very often who interact maybe primarily with other group members, but occasionally interact with non-group members. Might group structure play a role in the spread of norms? Let's find out. So, let's talk about group beneficial norms in a structured population. Let's consider, in this case, not one, but 2 groups. So, again, minimal assumptions of multiple groups is 2 groups. Within each group, things work just as before. Individuals will interact with group members, accumulate payoffs, and then observe another agent for success-biased social learning. If the groups never interact in any way, we'll just have two exact copies of our previous model. However, individuals do sometimes observe individuals from other groups through travel or trade or intermarriage, etc. Right? If a member of another group uses a different norm and is doing demonstrably better than you are, you might consider adopting their norm. This is the situation we will consider here. The mechanism of success-biased copying in a group-structured population provides the basis for a type of cultural group selection, in which group structure facilitates the spread of group beneficial norms. Or will it? Let's find out. Other mechanisms include migration and military conquest, and I'll discuss those in the further directions component. So given that norms might arise in a variety of ways, it's not unreasonable to assume that different groups will initially converge on different norms for fairly arbitrary reasons. We've seen that once a dominant norm is established, it can be difficult for a new norm, even a superior one, to spread within a population. However, if there's variation between groups, and if that variation is observable, a new norm might be able to cross boundaries. So, to set up this model, we're going to extend our grid and divide it into two, so that the group on the left will be separate from the group on the right. And we'll assign each agent a group ID in addition to a norm, so that it knows what group it's in. In principle, this model can be extended for an arbitrary number of groups, but we'll stick with just two in our analysis. So let's look at, go to the code, coordination underscore two groups dot nlogo for coordination with asymmetric payoffs and group structure. Okay, so here we've added a couple more sliders. Now we've got two init norm 1 sliders, one for group 1 and one for group 2. So that determines how many agents will use group 1 norm 1 initially in group 1 and in norm 2. And then here's our probability of outgroup observation. So let's set up the model. Notice here, 80% of group 1 uses norm 1, and only 10% of group 2 uses norm 1. Right. Let's look at the code. And this graph here is just the frequency of norm 1 in the total population. So a couple things have to happen. In setup, I'm dividing the space into group 1 and group territory. I've made the space larger and made all the patches on the left be a different color than the patches on the right, and so then I can use those colors to tell them what to do. And I made a middle patch, a middle column of patches gray that no agents will be on, just for visualization's sake. Then when I set up the turtles, the patches, all the patches that are color 1 or color 0 are going to produce agents, but I'm going to separate conditions, what shape and what norms are assigned to the groups into the agents in group 1 and group 2. After that, everything happens exactly the same as before in our previous versions of the model, except in our copy others procedure. So before, we just observed a random turtle. Like each agent, when it came time to copy another, it just picked some other turtle at random and observed them. Here, with probability equal to prob outgroup observation, it makes sure that it observes an individual in the other group rather than its own group. Otherwise, it observes a member of its own group. And that's the only thing that's different. Okay. So, it's always good to check our intuitions or check a model by using a scenario in which we know what should happen. So let's look where prob outgroup observation is 0. All right, what's going to happen is predictable. So we know that the threshold for norm 1 to spread is 0.33. So norm 1 is going to take over in this group, and norm 2 is going to take over in this group. Let's just make sure it happens. And it does. So now let's just increase the probability of outgroup observations. So just 1% of observations now are of outgroup members. And what we see is a little bit of persistence of norm 1 in group 2. Occasionally, norm 2 ends up in group 1 just by chance because it's probabilistic copying, but we see more of norm 1 in group 2 because it's the better norm. But 1% observation is not enough. Let's increase it to 2%. Now, see considerably more of norm 1 in group 2. I think if we wait long enough, norm 1 might end up spreading into group 2. I'm going to help it along by increasing the probability of outgroup observation. 3%. Beautiful. Okay, bam. Norm 1 spreads throughout group 2. So even a small amount, so 2 or 3% of interactions, of observations are without group members, can facilitate the rapid spread of group beneficial norms from one group to another. Unsurprisingly, you can also show that the higher the value of P star, the higher the threshold is, the more outgroup observation is required for the norm to spread from one group, from a group where it's common to one where it's rare. So, if individuals sometimes observe others from other groups and are willing to switch to any more successful strategy, then the group beneficial norm can spread even with a small amount of outgroup observation. Now, the model makes a couple of strong assumptions. It assumes that all interactions still occur within one's group, which is fine, but it also assumes, related to that, that individuals are willing to consider another's success as a reason to copy them, even if they are successful in a different social context. I think this is probably a reasonable assumption. Certainly not for everyone in all cases, but in some cases it will be, and it's important to consider when it would or would not be a reasonable assumption of copying. I can imagine sometimes where you might be unwilling to copy someone from another group regardless of how successful they are. Another strong assumption of the model is that both norms and their associated payoffs are easily observable. This might not always be the case. So if you've ever entered a new cultural environment, you probably know that the right way to behave isn't always obvious. And it's certainly not necessarily clear precisely which norms lead to a group success when many candidates are present. So a striking example of this is the cargo cults of the Pacific in the aftermath of World War II. If you don't know about these, look them up. They're really interesting. These are groups of islanders that were basically exploited by U.S. troops who used their islands as military bases. And after seeing how much stuff the Westerners had, they started copying arbitrary behaviors in hopes of getting similarly successful. So they constructed wooden air traffic control towers and performed pseudo-military drills emulating US soldiers in hopes of attaining similar levels of material wealth that never quite materialized. All right, that's the end of this unit. Most of this discussion was based on this paper from 2002 by Boyd and Richardson. It's a great paper. The title is Group Beneficial Norms Can Spread Rapidly in a Structured Population. But let's talk about future directions and other kinds of things that the study of norms and coordination can get us to think about. So one just a general topic is cultural group selection. So selection at the level of the group, if for those who've taken evolutionary biology, is controversial when considering the evolution of genetic traits, just because it's not clear how often conditions are met that allow for that kind of selection. But group selection is well established for cultural traits due to the normative nature of human psychology and culture. The model we looked at and considered here is just one approach to understanding how group structure and competition facilitates the evolution of cultural practices. And I've just highlighted a few papers here for further reading. Signals and markers. So many norms of behavior are opaque until one is already engaged in the interaction. If a person could express signals about their likely normative portfolio, those signals would enable more effective assortment on norms and more efficient coordination. An early treatment of this idea is provided by the economist Michael Spence in 1973, specifically in the context of how employers evaluate potential employees, but it's a good paper and has some very general principles about signaling. Others have shown that if individuals prefer to interact with those who share arbitrary markers, then markers can emerge to be associated with particular norms. Signaling can also facilitate the persistence of multiple norms in a population, with norm marker associations strongest near the boundaries between populations who hold differing norms. So more nuance and more richness of populations can be revealed by assuming more complexity of behavior like signals. Also, noisy signals and intergroup variation. Within populations, there can still be variation, but it's not always feasible to avoid those who don't share all your norms. Within a society, we sometimes have to interact with those who don't share our norms, and we may want to avoid signals that highlight those differences. So my colleagues and I have considered a couple types of signals, those sent overtly and covertly, and showed that covert signals should be dominant in cases where assortment is imperfect and uncertainty about shared norms between strangers is both high and consequential. There's a nice and I think related paper by Hoffman et al. Exploring conditions for intentionally noisy signals in which the act of obscuring is itself ascribed value. Language and conventions. So much of communication involves an issue of coordination. The need for linguistic signals to represent similar things to both sender and receiver. So in reality, language is obviously much more than a set of signaling conventions. Its most important feature is perhaps the flexibility to convey almost any idea. But its conventional aspect is nevertheless important to understand. Models have shown how repeated coordination games can give rise not only to shared signals, but shared categories, as with conventions for color names or safe versus dangerous foods. Okay, that concludes our unit on coordination and norms. Up next is our final modeling unit on socio-political cycles. Thanks for watching.